At this point, we have thought of trees as collections of keys. So if you think about it, all of the trees we've looked at have had a node which had a label associated with it, so an integer or string or whatever it was. And when we wanted to insert something into the tree, if it was a binary search tree, for example, we just found the correct spot to insert it based off of what this key was. Well, more generally, trees are useful when they can contain not only keys, but data associated with the keys. So for example, if you want to look up a tree node represented by the string tomorrow, then you can find the node tomorrow, and associated with tomorrow might be some extra data, which is the definition of the word tomorrow. Okay, so you can build dictionaries easily this way. You can do many applications. So typically, you don't just want to store keys themselves, but you want to store data associated with them. And our homework problem is another example of that. So I want to talk a little bit about the ways in which we store data associated with these keys. And I'm not going over the notes exhaustively. I'm going to pick and choose and hit the key points. And then I really want to focus you on what you'll need to know to be able to do the homework problem with minimal pain. So let me share my notes. So we've assumed that the data we're searching for is the search key to this point, but often that is not the case. And we want to make a distinction between key and value or data associated with the key. So I made the example in the intro of word definition pairs, many other examples, but this is a common use of trees that we want to be able to have a strategy for. We might want to look up an employee record, for example, if we key their social security number. So we need to distinguish key and data. Keys are ordered. There's some way to say which key is bigger than which other key. The data can be anything. It's the kind of thing we want to represent, like in the list, most generally by a void pointer. And oftentimes the data can encode a lot of information. They could be large records. They could be entire books. So we want to think about a way of doing this efficiently. Now that said, we don't have to always build a key like a tree, like I said before, in the most abstract general way. It's perfectly fine to cobble a tree together that's specific to our application, because C makes it very easy with recursion and with pointers and structures to be able to do tree operations. So I'm going to talk about two different approaches to associating data with keys. And I do this because I think one of them is something that you've never seen before, most likely, and it's clever and has some very nice properties. I'm not going to go into it in depth just yet because we're still going to use the more traditional model for the homework problem, or at least I strongly recommend it. So in the two approaches, I'm going to call them Model 1 and Model 2. And the difference is, well, there are several differences, but the first difference, which I show on the slide, is in Model 1, you don't ever ask if you have found the key when you are searching for it. Okay, so there are only two possibilities. If the key that you are searching is greater, is less than the node key that you are currently visiting, then you take the right branch until you reach a leaf. Otherwise, you take a left branch. You never ask if it's equal, so you only have to do two comparisons. All the objects associated with the keys are stored in leaf nodes. So that's why you don't test for equality. You don't say, am I at the key now? If so, take the data, because the data is all in the leaf. So I have a depiction of this a couple slides from now. In Model 2, which is the one that's more intuitive and the one you're more accustomed to, you go left if the query key is smaller than the node key, right if it's greater than it. But if the query key is the node key, then you just take the data, because the data is stored with the key. If we want to ask what the consequences are of one model versus the other, in Model 1, one of the advantages is for being able to do analysis, for being able to do proofs of bounds of certain properties that are important when you're doing tree construction and tree manipulation. So the underlying tree is always a binary tree, not a ternary tree with a third node, which is an object. Turns out to be a very nice property, as opposed to Model 2, where each node has a special middle neighbor. In Model 1, each interior node has a left and right subtree. In Model 2, a left or right subtree might be missing. That also can complicate the analysis. So there are some reasons why model one is cleaner, even if it's counterintuitive. Okay, so you might say, well, it's going to take much longer because all of the nodes require you to traverse to a leaf. Well, you have to also remember that most of the nodes are toward the bottom of the tree in the Model 2 tree as well. So it's a little counterintuitive, but it's not quite it's not as bad as you would imagine. So in Model 1, traversing an interior node requires only one comparison. That's a performance advantage, albeit small. In Model 2, we need to do two comparisons to check the three possibilities, equality as well. In a Model 2, like I said, we can reach an object earlier, but it's not as big an advantage as it might seem because of the fact that the number of elements doubles at each level. Okay, so it's easiest seen with a simple example. This is the Model 1 tree where all of the interior nodes are keys and where the objects associated with those keys are stored as leaf nodes. So you can see that every key, 1 through 9, has the data associated with it. It's all just stored at the bottom. And the price you pay is in the construction of these trees, which I outline in great depth in the notes. It's kind of clever. You might have, and often very frequently, you have a duplicate key, but that's the most you could have. So the algorithmic complexity doesn't increase, it's just a constant. And it asymptotically doesn't make much of a difference as the data sets get very big. So for example, if you wanted to search for the data associated with the key 3, you'd start at 5 and say, well, 3 is less than 5. Well, 3 is not less than 3. So you go to 4. 3 is less than 4. Are you at a leaf node? Yes. Take the object. And there's a convention for having the other child node be null. And that's how you know you're at a leaf node. Okay. So this nicely organizes all of the data outside of the organization of the keys in the tree. The one that you are more accustomed to and the one that I would strongly recommend use on the homework because the advantages aren't really clear in the application I gave you to work on. You have the data associated with each key, and then you simply say, is 5 less than 3? Yes. I'm sorry, is 3 less than 5? Yes. Is 3 less than 3? No. Is it equal to 3? Yes. Okay, take the data. Okay. And so like I said earlier, you can have incomplete nodes and each of the nodes themselves is no longer binary. Okay. So we can talk a little bit more about that later. I do show how to construct such keys and give some bounds on the tree height for each of the different models. And that's something that we'll look at in a little bit, but I want to get to some key points to allow you to do your homework problem first. And some of the notes I'll just let you look at yourself. Some of them, as I'll give you a warning on, will be subjects on the quiz. And some of them I will do in a later segment that's recorded. So let me talk about traversing the nodes of a tree, which now is, we can just think of the Model 2 tree for simplicity's sake, because remember when we're doing the Barnes-Hut algorithm, we have to associate data with each of the nodes in the tree. The nodes in the tree represent squares or sub segments of physical space, and there's data associated with them. You're going to put particles in the tree. You're going to have the bounds of the domain that particular tree node represents. There's going to be a whole bunch of stuff that you're storing in addition to the pointers to the children. And it being a quad tree, you're going to have 4 children pointers. So what I'm going to show you here is going to be not exactly the same, but analogous to the case of a quad tree. And I'll point out where it differs. It's very, very, very little. Okay, so traversing the tree is important because it forms the foundation for a lot of things that you're going to need to do in Barnes-Hut. So if you traverse the tree, you can easily turn the tree into a list. You can find things that you want to find in the tree. You can prune the tree. It's kind of the foundation for a lot of tree manipulations that you are going to have to be able to do. And just in general, once you build a tree and stuff data in a tree, you need to be able to move around the tree with facility in order to do a huge range of operations. Okay, so there are three common ways to traverse the tree, and each of them has a very simple recursive implementation. Or if you prefer not to do it with recursion, you could do it with a simple data structure like a stack. Okay, I think for a tree operation using recursion, even in an HPC code, is fine. You got to be a little careful, but it tends to be a relatively simple operation relative to, for example, iterating over the list of particles in performing like a force calculation. But anyhow, that's maybe too much of a detail right now. Let's just talk about what these different methods do. So pre-order, okay? Uh, the way to think of these things is that they define a sequence of operations on a parent and two children for a binary tree. And then when you consider a more complex binary tree that has more children, the same pattern holds recursively. So what do I mean by that? Well, if we just consider F, B, and G, a pre-order traversal would be F, then B, and then G. Okay, so it's root, then left, and then right. Okay, so the nice thing recursively is if you want to express that for the tree as a whole, you can say, when I say visit, just imagine you're doing something. You could just think of printing it for simplicity. So say I'm going to print the starting node. Let's say I start with F. So print F, and then recursively call pre-order on its left child, and then recursively call pre-order on its right child. Well, if the tree were just FBG, that would just be FBG. But since it's done recursively, you're going to do F, then B, then A, then D, then C, then E, then G, then I, then H. Okay, but you only need this much code to do it. And if you prefer to explicitly keep a record of the nodes that you have passed but haven't visited yet, the way to do it is by pushing on the stack, okay, and then popping off of the stack after you make it all the way to the bottom. So it, I guess it's a matter of preference. I prefer to do it this way because I'll give an example. If you're doing a pre-order traversal of a quad tree, then it would look exactly the same, except you'd say pre-order node dot child 0, pre-order node dot child 1, pre-order node dot child 2, pre-order node dot child 3. And you would have 4 nodes for a quad tree, and it would do the exact same algorithm without having to deal with all of this stuff. Okay, so there's no right way, but just look carefully at this code and make sure you convince yourself it's the same as this code. And let's see if I got it right. F, B, A, D, C, E, G, I, H. Okay, let's see what's next. Okay, the next traversal type is called in order. And in order is nice because it's a simple way to determine that it's a valid BST, because if you do an in order traversal, the keys should come out in increasing order. Okay, and the way to think of it is the same way as the other one. Think of it with just 3 nodes. And if you had just those 3, it would be in order node develop. So it would be B, then F, and then G. You see those would be in increasing order. But then you're doing it recursively. Okay, so you're calling in order node dot left, then print or visit the node, then in order node dot right. So if you did that, you would start with left, but then you do it recursively. So you start left, so you'd be here, A, and then you're done. So the middle comes next, B, and then comes the right, but you have to do it recursively. So C, and then you're done. So it is the middle, D, and then the right, E. I'm sure many of you have seen this before. And then now you have to process the right side of F, which is G. Then you go right, but you have to do it recursively. So H and then I. So this is rigged so that it goes in alphabetical order. And that is what would have to happen if these keys were sorted by character in the alphabet, if they're sorted alphabetically. Okay. And so you see, you could also use a stack, but it's much more expressive to do it this way. And just like with the other one, with the binary tree, well, um, this isn't something that we're going to have to use for the binary tree traversal on the homework, so I wouldn't worry about it. But there's a similar extension to a binary tree. Okay. The last one is, let's see if, yeah, we got it right. The last one is post-order traversal. Okay, so post-order, we're going to think of it the same way, where we think of three nodes and we do left and then right, and then we print the node. So this is just B, G, and then you print the root node last. Okay. In this case, the non-recursive code is considerably more complex. So it's probably worth it to get used to doing it this way. So it's just, we go left, left, so it's A, and the roots last, so it's A, C, E, D, B, H, I, G, F, right? So the roots last. So let's see if we got that right. A, C, E, D, B, H, I, G, F. Yeah. So if that's not clear, just go through it slowly one time and you'll get used to it. And so you definitely want facility with these types of operations. On an interview, you probably wouldn't get a binary tree, maybe, but they would try to give you a slight twist and make sure you could extend the recursive algorithm. So it's good to pull out a pen and paper if you're not used to these things and get used to not having to do every operation in your head, but just sort of see the pattern and be able to reproduce it quickly. So a lot of the rest of the notes are devoted to understanding how to program the Model 1 trees, particularly how to do find and delete operations, and showing what conventions we can use in C to be able to implement them. So there are just certain little tricks we use to be able to quickly manipulate them. And I think it's very interesting, and I will do a segment on it where we cover that. But before that, I want to make sure I do a considerable segment on the homework problem, because the high level guidance I gave you and the Barnes-Hut slides probably aren't enough to really understand the algorithm. So I want to be able to lay out some pseudocode. I want to be able to show you a little code, give you some direction of how to start, sort of tell you the things in the notes that you should make sure you understand to be able to extend them to the code. And then when I wrap that up, I will do a last segment where we go over some of these Model 1 trees, and maybe we'll have a quiz question or two on them, or I'll give you a chance a little bit later to manipulate them. And in the past, I've, in some courses, had big problem sets on Model 1 trees. In other cases, we've ignored them entirely. I'll probably do something in between in this class, but I felt like Barnes-Hut was a really good way to synthesize a lot of concepts that we've done to this point. So my next segment will be directly related to the homework.